Hi everyone, I think we can start. I started the recording as usual, so if you need it, just ask by mail and we will provide you the link. So this is Alfredo. I will take care of this session, part 4. Last time my colleague Matteo shown how to use a user interface to navigate the data, to do the analysis, to check the alerts, get notified, etc. Today, we will see, and he was using the capture on a standard interface. Today, we will see how to integrate ntopng with our software probes, like a probe, to collect data from remote locations, from routers, switches, and how to integrate ntopng with ntodisk, which is our traffic recorder. And we will also see a little bit of performance and tuning. So let's start with this session. So first of all, I want to recap what we have seen in the first session about all the options that we have in terms of technologies and techniques to get traffic information. So we have seen that we have coarse-grained and fine-grained techniques that include counters, flows, and packets. So we have seen that we can get traffic information in terms just of counters and port status, for instance, from using SNMP. We can get traffic information using net flow from routers and switches. We have seen that we can extract information directly from packets. So we need to select one of those technologies or a combination of them in order to find what is the best technology in our use case, based on our requirements, based on the resources that we have, because, for instance, analyzing packets is more expensive than analyzing flows or even counters, because we have to extract information from all the packets and somehow summarize them. Instead, reading just counters using SNMP is really cheap because we just have to query the device and get some counters. Or we can use flows, which is already a way of cluster to extract information from packets. So we get already metadata from the traffic, and this requires less resources. So depending also actually on the money that we are ready to spend and the power that we are ready to use for even running a box able to analyze the traffic, we can select a different technology, or also based on the equipment that we have, the devices that we have in our network. So if we have a router able to export net flow, we can just collect net flow. If we don't have it, we have to use software probe or ntopng directly and analyze the traffic from a mirror, for instance. Of course, if we decide to analyze net flow, you have to remember that, bear in mind that we don't have, we may miss information like layer 7 metadata, because standard net flow usually provides for each flow just packets and bytes and little more information. Instead, if you want to have visibility on layer 7, like for HTTP, you want to see the URL, the server name, those information, we need to use a software probe like mprobe, that includes the packet inspection engine and is able to extract those information. So let's recap what is a flow. So a flow is a way to summarize packet information. So a flow identifies a network communication, for instance, all the packets required to download a web page, or for a call, a voice over IP call, all those packets belong to the same flow, which is identified by source destination IP, source destination port, the protocol, and the VLAN. Maybe it depends on the case. And so a flow identifies a network communication. So we have seen that in Wireshark, when we capture the traffic, we can filter for a specific communication, like in this case, which is an HTTP request, where we have seen CAC and a request and some data returned by the web server. This can be summarized into a single line that represents a flow with the metadata. So we can see the client IP address, client port, server name, and port for HTTP, the duration of the communication, some metadata like the URL, and then we have additional metadata if we go into the flow information. Now, how to get those flows? So how to get, if you have some, our network that consists, of course, of packets, how to get the flow information? So we say that we can get the flow information using NetFlow from routers, or we can use a software probe like mprobe or mprobe CentOS. So a software probe is able to, in case of NetFlow, you can use it both for collecting NetFlow from routers or for processing packets. In case of mprobe CentOS, this is for processing packets only. The difference between the two is that mprobe CentOS is able to scale up to 100 gigabit, but of course it has less features than mprobe, so it can extract less metadata than mprobe. So they are, let's say, packet classifiers, and so you can use them on live traffic to extract flow information and export those information to a database, to ntopng, or in other formats that we will see. Then there are other options, but I want to focus on mprobe right now. So in the first session, we've seen that ntopng can ingest traffic information using packets from a network interface or a pickup file, counters from SNMP. In this case, it just shows you the packets and bytes on a switch or on a switch port, or can collect, again, flows that from mprobe, which is our probe, or mprobe CentOS. And this traffic information is provided using flows over ZRMQ. We will see what is ZRMQ. And mprobe can, as we said before, process packets. So if you have a network interface where you receive traffic from a mirror port or a tap, you can process those packets and extract flow information and send information to ntopng. Or you can use mprobe to collect NetFlow IPFix as flow, receive those information and send those information again to ntopng using this ZRMQ channel. As we said, if you run mprobe on packets, you can extract layer 7 information, because in this case, mprobe has access to the packet payload. So we can use our deep packet inspection library to inspect payloads and extract like the URL for HTTP as an example. Instead, if you collect NetFlow from routers and switches, mprobe receives flow information, usually 5-tuple packets and bytes. So we are not able to extract layer 7 information in this case. We can just guess what is the layer 7 protocol based on the port number, protocol and port. But we are not able to be really precise and detect what is the actual protocol based on the packet payload, because we don't have visibility on the packet payload. We don't receive the packet payload from the probe. Just a second. I see a question in the chat. What is the difference between mprobe and mprobe CentOS? I guess this was before my explanation. So the difference, as I said, is that mprobe CentOS is faster, able to scale up to 100 gigabit, but less feature rich. So you have, for instance, in mprobe, we have plugins to extract information from radius, diameter, specific traffic, even HTTP. With mprobe CentOS, we're able to export information for selected protocols, and they are limited. Like for HTTP, with mprobe CentOS, we can export information, but they are less than those exported using mprobe. So with mprobe CentOS, for instance, we export just the URL, a few more fields. Okay, welcome. So please, if I don't see some question in the chat, please open the microphone and ask. Okay, so when you have to collect NetFlow, you have to use mprobe. We don't collect NetFlow directly in ntopng for a few reasons, mainly because mprobe has several dialects, so the logic for implementing a NetFlow collector, it's not that simple. So we decided to keep all this intelligence into a single probe, in a single place, let's say. So if you have to collect NetFlow or NetFlow dialects, like the Cisco ASA, you use mprobe, which is receiving NetFlow and converting this information in JSON and send this to ntopng. Actually, we use JSON or other more optimized formats. We are able to export like TLV over 0MQ, which is the binary format, or we're able to export JSON over Kafka, for instance. So we have several formats and communication channels. So mprobe can, as we said, analyze packets, and in this case, you can analyze packets up to, let's say, 10 gigabit per second on a single machine using mprobe. If you want to scale to more than 10 gigabit per second, you probably need mprobe CentOS, which is able to scale up to 100 gigabit per second. Of course, you need adequate hardware. You need a network adapter, which is fast enough to handle that rate, but this is another discussion. In addition to packets, can collect NetFlow, V5, V9, IPFix, SFlow that you can generate from switches and routers, as we have seen in the first session. It can export this data, so the flow metadata, to ntopng, and using 0MQ or Kafka. Can export flow information also in NetFlow, V5, V9, IPFix, or can store this data to disk in text files, CSV files, also compressed, to databases like MySQL or ClickHouse, to Elasticsearch. So we have many export formats. And mprobe, also ntopng, they include NDPI, which is our deep packet inspection engine, which is able to detect hundreds of application protocols. So for each network communication, this library is able to tell you if this is Facebook, YouTube, whatever. And of course, it supports IPv4, 6, many encapsulations, VXLAN, MPLS, GTP, GRE, GTP v1, v2. So we support most of the traffic that you may have on LAN or internet or mobile networks. So this is the big picture. So as we said, we can get packets for NetFlow and export NetFlow to other collectors, or flow in 0MQ to ntopng or Kafka. We can store to ClickHouse, Elastic, MySQL, or text files. So we have seen that we have many features, so we can run mprobe. It's really flexible, and we can run mprobe in several combinations. For instance, we can collect, process packets and export NetFlow, or we can collect NetFlow and export NetFlow, so acting as a proxy, or we can collect NetFlow and export the data to disk or database or ntopng, of course. As usual, please stop me if I go too fast and ask. So let's see how to configure mprob with ntopng to collect NetFlow or to process packets. So let's see, for instance, what we call the collector mode. So collector means collecting NetFlow. So in this case, we have mprob, which is collecting NetFlow, flow information from routers or switches, and send this information to ntopng using ZeroMQ. In order to do this, now I will show you examples using the command line, but you can do the same using the configuration file. So we have seen in the second session how to create a configuration file like etc mprob.conf or etc ntopng.conf that contains all the options, one per line, where we have the parameter equal the value, parameter equal value, one per line. So in this case, I will show you the command line because it's easier, but you can run the same as a service, creating a configuration file with the same options. So in this case, we have mprob, and we specify that as ingress interface for packets, there is none. So we are not processing packets. We are collecting NetFlow. So we specify the collector port 255, which is what we configure in our router when configuring the NetFlow export. So this is to tell mprob that we are collecting flows, and then we specify the ZeroMQ endpoint where ntopng will connect to receive the flows. On the other hand, we have ntopng, which has been configured with the ZeroMQ endpoint where ntopng should connect to get flow information. So we have mprob collecting NetFlow and ntopng connecting to mprob to receive the flow information. This is the collector mode. Then we have the probe mode. Probe means processing live traffic. So in this case, you have mprob, which is receiving traffic packets from a mirror port of a switch, so a spam port or a tap device. This is processing the traffic and extracting flow information and exporting flow information over ZeroMQ and ntopng. So in this case, the configuration will be mprob-i interface ETH1, which is the interface where mprob will receive the packets. So this is where you will connect the mirror port from the switch. As collector port, you specify none. That means that we are not collecting NetFlow, but we are actually processing packets from ETH1. And then you specify, again, as usual, the ZeroMQ endpoint where ntopng will connect to get packet flow information. Now here we also specify what we call the template. The template is the set of information elements that you want to export. So usually here you specify that you want to export. So this specifies the flow metadata, the flow information that you want to export. So for instance, this is usually a list of source IP address, destination IP address, source port, destination port, protocol, in bytes, out bytes, in packets, out packets. There are standard information elements from NetFlow and additional information elements that we defined at ntop. When you specify at ntopng at, this is a shortcut for the set of information elements that ntopng is able to understand. So you don't have to specify manually all the information elements that you want to export, so to extract from packets, but you specify this shortcut area. This makes sure that all the information that ntopng is able to understand from mprob, they are extracted from packets and exported. So this is a standard line, configuration line. On the other side, the ntopng configuration is the same. So you specify again the ZeroMQ endpoint where ntopng will connect to get the data. So with ZRMQ, what happens is that mprob connects to ntopng, or ntopng connects to mprob according to the configuration. I will show you later that we have the two options. And mprob will start sending this data to ntopng in JSON format or in TLV format. Actually, TLV is the default, which is a binary format that compresses a little bit the data. Why we use ZRMQ? Because this is a simple messaging system that automatically handles disconnections. So when you don't have to care about if you run a probe first or ntopng first, or if one of the two disconnects, it automatically handles the reconnections. And it's a really nice channel for sending the data, because you can also have multiple producers or subscribers. I will show you a few use cases in a moment. And we are also able on ZRMQ to compress the data and also to encrypt the data optionally. Especially if you have to move traffic information from a network to another, crossing a public network, it's nice to have the encryption. The encryption in this case is using a native encryption support in ZRMQ, which is the curve encryption. In order to enable the encryption, you have to add this option to ntopng, so --ZRMQ-encryption. And as a consequence, in ntopng, in the user interface, you will see something like this, that in essence, ntopng will print the public key that you should configure in mprob. It provides also, ntopng provides an example here of configuration that you should use for mprob. So in essence, ntopng generates a public and private key. The private key, of course, is internal to ntopng. The public key is something that you configure in mprob using this option to make sure that mprob will be the only one able to decrypt the data. So, yeah. No, sorry. Yeah, it was the other way around. So mprob encrypt the data, and ntopng is the only one able to decrypt the data. So this is, again, the examples that we have seen before. So if you want to enable the encryption, you run ntopng. You specify the TCP, the ZRMQ endpoint over TCP, where ntopng will connect to get the data, and you specify that you want the encryption. Then you go into ntopng, you get the encryption key, and you add it to mprob, like in this case. So here you configure mprob with an interface, the ZRMQ endpoint, and the ZRMQ encryption key. So in this case, mprob will extract the data, encrypt the data using this public key, and ntopng will receive the data and is the only one able to decrypt the data. You can do the same using the configuration file, as we said. So if you want to use the configuration file to run the ntopng and mprob as services, you can specify under etc ntopng.conf the ZRMQ endpoint, under etc mprob.conf the mprob configuration, so the network interface and the ZRMQ endpoint, and you just restart the services. And this will apply the changes to the configuration. Now, what you have seen now is what we call the poll mode. That means that ntopng connects to mprob to get the data. In fact, if you see the configuration, the command line configuration, so we have a parameter in mprob where we specify that we want to export the data on ZRMQ, and we listen on port 5556 on any IP address of the machine. So you can notice this star. And then ntopng will connect to the IP address of the machine running mprobe on port 5556 and get the data. This means that ntopng connects to mprobe, and mprobe sends the data on this channel. Now, this allows us to have multiple ntopng connecting to the same mprobe to fetch the data. So this is the advantage of this configuration, which is the default one. Now, there is another option. The other option is to use what we call the push mode. With the push mode, mprobe connects to ntopng and sends the data to ntopng. In this configuration, you cannot have multiple ntopng connecting to mprobe because it's mprobe that is configured to connect to ntopng. But if you are running mprobe behind a NAT, for instance, or a firewall, this is the only configuration you can use because ntopng cannot connect to mprobe because it's behind a NAT, but mprobe, in this case, can connect to ntopng. So depending on your topology, you may choose one option or the other. The result is the same. So mprobe is always sending flow information to ntopng, but who initiates the connection makes the difference. So in this case, it's ntopng that connects to mprobe. In this other case, it's mprobe that connects to ntopng. And of course, in this case, as we said, you cannot have multiple ntopng receiving the same data from the same probe, but you can have, for instance, multiple probes sending data to the same ntopng. So you can have a single ntopng with a single ZRMQ endpoint, which is collecting flow information from multiple probes distributed in your network. In order to configure this push mode, you have to add this suffix to the ntopng, to the ZRMQ endpoint in ntopng. So ntopng in this case is listening on this port, and in mprobe you configure again the ZRMQ endpoint of ntopng, and you specify that mprobe is running in probe mode. So you specify that mprobe is a probe that should connect to ntopng. Is everything clear? So here there is an example with the same command lines that we have seen, or that shows the poll versus the push modes. So in this case, again, ntopng connects to mprobe. In this other case, mprobe connects to ntopng, and as you can see in this example, you can have multiple probes, like in this case, you have two probes capturing from two different interfaces, sending to the same ZRMQ endpoint. This is the push mode. Okay, now let's see the observation points. So we have seen that we can have multiple probes sending the data flow information to the same ntopng instance. In this case, you can introduce the observation points, which is a standard. It's defined in IPFix as an observation point is a location in the network as defined by IPFix, where we can observe the network traffic. For instance, let me show you a picture. If we have ntopng, which is receiving flow information from multiple probes in a distributed network, we may have our network can be distributed in several locations. Like in this case, we see 3 different cities like Rome, Paris, and Berlin. And we have, in this case, multiple probes for each location. So we can define what is the observation point in this case using a different ID for the observation point for each location. So for Rome, we have the observation point 1234. For Paris, we have 1235. From Berlin, we have 1236. This is useful when, again, when we have to collect the data from multiple locations, and we have hundreds of locations, for instance. And we want to see a view of the aggregated data. So we aggregate everything in a single ntopng instance. But at the same time, we want to have a view of the traffic for each location. In this case, we can use ntopng to identify the traffic based on the location. We will see how to do that. First of all, the configuration. So in order to configure the observation points, when you run a probe, when you run each probe, you specify an ID for each observation point. For instance, for all the probes in the first site, so in ROM, for instance, I specify this option, which is -E uppercase 1234, which is the observation point ID. For all the probes in Paris, we specify observation point 1235. So you can, as you can see, we have multiple probes in this location, and we specify the same observation point. This information is propagated to ntopng. So ntopng knows that all the traffic received by this probe, from this probe, belongs to site B. So let's see, for instance, ntopng. ntopng, when we receive this observation point information, we are able to, first of all, show you this new drop down. So we have the interface that we are analyzing, in this case, the ZMQ endpoint. And for the interface, we also have this other drop down where we can select the observation point. So the location that we are analyzing. So for instance, if we want to see all the flows that our probes see in ROM, we select here ROM. If we navigate the user interface, the ntopng user interface, under the flows page, we see the flows which are from ROM. And if we select a specific network communication, we see the observation point information that is reporting that this flow has been seen in ROM. There are also other pages in ntopng. If you go under the flow exporters menu, there is a page which is observation points, where we can see for all the locations in our network, so for Rome and Paris in this case, some statistics like the current traffic throughput, the total traffic that we're seeing, the number of hosts, and charts. So for each location, we can analyze this traffic and see what are, I don't know, the top application for that location, and the traffic for that location, and many other metrics. For instance, for each layer 7 application like Facebook, Amazon, we can see the traffic over time. Any question? Because we are going to change the topic now. So let's say observation points are useful when you have a really large network in many locations and you don't want to put everything in a single view, or you want to have a single view, but you want then, when analyzing the traffic, you want at some point to drill down and see what is the traffic in a single location of your distributed network. Okay, I don't see questions, so I will go ahead in the next topic. So we have seen the integration of ntopng with mprobe. Now I want to show you how to integrate ntopng with N2Disk to implement what we call the continuous traffic recording. So why we need the continuous recording? Because with ntopng, if you analyze live traffic directly or through mprobe, or if we collect NetFlow using mprobe, we have summarized information, actually pretty detailed, like we can see all the network communications, metric about the network communications, etc. But in some cases, it is required to drill down up to the packet level. So we have seen in a previous slide that with Wireshark, for instance, we can analyze the traffic at the packet level, so see all the single packets for network communication. We can open, we can drill down and analyze a single packet and check the packet content, payload, and check the hex, for instance, check all the bytes for all the packets. And this is sometimes required when analyzing security events or troubleshooting. The problem is that if we want to look at packets, we cannot do that manually because on a high-speed network, it's too overwhelming, too complicated to do for an analyst. So we have to leave the traffic flow and analyze it using probe and ntopng. And when something happens, we want to drill down for that specific network communication and check the packets. But it's not possible to predict when this event happens in the network. So we don't know when this happens to open Wireshark and put a filter and analyze it. So we need a way to record this network traffic. And we cannot record the network traffic forever because it's a lot of data. For instance, at 10 gigabit per second, we have around 1 gigabytes per second of data to store on disk. So you can imagine that you need a really large storage. So what we can do is to record this data similar to the 24/7 camera, where we have a window, a sliding window with the recorded data for the last hours, day, 1 month. It depends. It depends on the traffic rate, traffic speed, and the storage size that you have. So based on the traffic speed, we can compute what is the storage that we need based on the data retention that we need. So based on that, we can tune the system to keep, for instance, if you want to keep the last day, we configure the system with enough storage to keep the last day. And our software, in this case ntodisk, can dump the traffic to disk. When the disk is full, it starts deleting the old data to make room for the new data. For this reason, we have this sliding window, because we have this window moving, deleting old data and dumping the fresh data. And ntodisk is doing this up to 100 gigabit per second. We use the pickup file format for dumping the data to disk, so that you can, the pickup is the standard, de facto standard format used by all the network tools like Wireshark, TCP dump, Snort, or even ntopng itself to store and analyze the traffic. So we use a standard format in combination with other file formats for indexing this data. But the packet, raw packets format is standard pickup. And okay, let's see how to configure ntopng to integrate with ntodisk. This means that ntopng should be able to be aware that ntodisk is dumping data to disk, and when something happens, we want to drill down and get the pickup files with the data. This is what we call the simple configuration. So you can go in ntopng. I will show you on a live system. So we can go in ntopng, select an interface, go into interface. We have this icon, which is traffic recording. And here we can enable the continuous traffic recording, specify the maximum disk space that you want to use. Again, I will show you later how to compute what is the disk space that you need based on the data retention and the traffic speed, the average traffic speed that you have in your network. We can specify also a capture filter if you want to discard, for instance, specific traffic. for instance, I don't know, if we have a storage system which is generating a lot of traffic in the network and we don't want to record that data, we can specify a BPF here, like not host 1, 2, 3, 4. So we save, and ntopng will automatically start an ntdisk instance which is recording this data. So this is what we call the simple configuration. So in essence, we have ntopng, which is capturing traffic from network interface, and using this menu that we have seen, ntopng will create automatically an ntdisk configuration, will start the ntdisk service, and at this point, we are able to also extract the traffic that ntdisk is dumping to disk. Okay, before showing you how to extract the traffic, I want to show you also what is the other option. So the other option is to, why we call it simple configuration, because we can use this configuration when we are processing traffic from a network interface using standard drivers. Of course, we cannot do this when we are collecting flows, for instance, because we don't have packets for the same traffic coming to this box, because we are collecting flows coming from another box. So the simple configuration is available only when capturing live traffic from network interface, and we are not using optimized driver like zero copy drivers. In this case, we can just enable the recording, set the maximum disk space, and filter, and that's it. If you need additional configurations or more advanced configurations, or we want to use another specialized adapter, for instance, that doesn't allow you, for instance, to open the same adapter using ntdisk and ntopng. So if you want to, let's say, create an enhanced configuration, we have to use the other option, which is configuring ntdisk manually using the configuration file, similar to what we have seen with ntopng and nprobe. So you create a configuration file under etc ntdisk.conf, you run it, and then you go inside ntopng and you select that ntdisk instance as an external provider. So instead of configuring ntdisk here, you tell to ntopng using this setting that you want to use an external ntdisk configuration to be able to drill down and get the pickup data using the external instance. So in that case, in essence, you can have ntopng, which is receiving traffic information using ZRMQ or any other source. You configure ntdisk as a external provider, and then you're able to run extractions from the pickup data stored by ntdisk directly in ntopng. Okay, let me show you how to do this, so to run the extractions. So after configuring ntdisk using the simple configuration or as external provider, if you go in any chart, for instance, in ntopng, you can notice here that there is a button which is download pickup. So you can select the time interval that you want. You click on download pickup, and you can use this menu to actually get the pickup file with the traffic matching this time interval, and also specify a filter. So I want to get the traffic in this time interval, but just for this IP address, or for this IP address and port 80, for instance. In a similar way, you can also go, for instance, if you have ClickHouse enabled, then you have the historical flows. You can select a specific network communication and click and download the pickup file. So let me show you. So I click download. This is downloading a pickup file, and I can open it. Let's see. So you have this pickup file that I just downloaded, and I can open it with Wireshark. So you can see this is the same communication that we have here, but here we are able to check every single packet for that communication. And same way we can go, for instance, to the alerts. We can go to alerts, I don't know, flow alerts, select a specific one, and click download pickup. So if ntopng detects an event which is triggering an alert, I can go here and get the pickup file and analyze it with Wireshark. Okay, so we have seen that we can use the user interface to drill down and download pickup data from historical data, alerts, flows, etc. Or we can also use other APIs, let's say, to download, to extract the data. So for instance, we can use the REST API that we have in ntopng. So in this case, we use curl with user and password of ntopng, HTTP REST get pickup live instruction, where we specify the network interface, the time interval, so epoch begin, epoch end, and a BPF filter. And ntopng generates a pickup file and we download it. Or we can use a command line API. So we have this tool, which is a pickup extract, where we specify the root folder where the pickup data is stored into disk. And again, the begin time, end time, a BPF filter, and we get the pickup file. So we have several options to get the pickup data. Any question about into disk and the recording? Okay, we go ahead. Now let's talk a little bit about the sizing. So I say that the storage size depends on the storage size that you need, let's say, for storing the data, depends on the traffic rate, so the link speed and or the average rate for the traffic that you have, and what is the size of the window that you need, the time window. So if you want to keep the data for the last 2 hours, for the last day, etc. If you consider 1 gigabit per second of traffic throughput, or a 1 gigabit link, but usually if you have 1 gigabit link, you don't have it fully loaded. For instance, you have half a gigabit. So let's consider, for example, a 10 gigabit link with 1 gigabit of average data rate. So in this case, you can have up to 120 megabytes per second of data to be dumped on disk, which is half a terabyte per hour, which is 10 terabytes per day. So if you have a link that you want to monitor with an average traffic rate of 1 gigabit per second, and you want to keep the last 2 days of data, for instance, you need at least a storage system with 20 terabytes. Then you have also to consider what is the throughput, I mean the traffic speed, because your storage system should be fast enough to be able to keep up with the traffic rate. If you consider a standard spinning disk, it should be able to dump, at least in our experience, an average disk is able to dump 1-2 gigabit per second in terms of speed. Then you have also to consider again the disk size, as we've seen here. If you have to dump traffic at 10 gigabit, that means that you usually need to use like a RAID controller with 8-10 disks, unless you use SSDs. In that case, probably 3-4 disks in terms of speed is enough. Then again, you have to consider the size of the disk. If you have to dump traffic at 100 gigabit, you probably cannot use spinning disks. We usually use NVMe disks, which are SSDs, which are directly connected to the PCI bus. And in that case, at 100 gigabit, you need at least 8 of those disks, which are really fast. A single disk is able to dump up to 10 gigabit per second in terms of speed. But of course, at 100 gigabit per second, you have a lot of data, so you need many disks anyway. Okay, so that's all about the continuous recording. Now, the last topic for today is about performance and tuning. Any questions till now? Okay, I will go ahead. So, first of all, talking about tuning, if you run ntopng, we have seen last time that, let me open again our system. So ntopng is monitoring the network and is keeping information about all the network communications, so all the active flows and all the not active hosts. So here you can see, for instance, number of active communications. So this is an idle system, so we have really few network communications, and the number of hosts here. So ntopng is keeping information about flows and hosts in memory. This means that if you have many flows and many hosts, you have to tune the system to be able to keep all those hosts and flows in memory, because in ntopng we have what we call the host cache and the flows cache. So there are two tables where we keep track of all the hosts and flows, and those tables, they have maximum size, maximum number of hosts and flows that they can keep. So by default, the size of the tables is large enough to work with small and medium networks. But if you have a big network with many flows, many hosts, you probably need to tune it. In order to do that, you can use the -x lowercase and -x uppercase options. And it's a good practice to set them at least double the size, the number of hosts and flows that you have in your network. For instance, if you have 10,000 hosts and 20,000 flows, you should add to the ntopng configuration file -x equal at least double the number of hosts. In this case, it's 10 times the number of hosts, but like 20,000 here would be enough. And the same for the number of flows. So the idea is that you run ntopng, you take a look at the numbers here, and you configure these accordingly. Now, ntopng should warn you about if you have the number of flows which is exceeding the size of this flow cache. You should get a pop-up or something like that. So when you see that, it means that you have to, it's time to tune the configuration. So this is about the memory. Then let's talk a little bit about the packet capture. So if you have ntopng capturing traffic from a network interface, or mprob capturing traffic from a network interface, if you have up to 1 gigabit per second, you probably don't need to do much tuning on the packet capture side. But if you have more than 1 gigabit, like 10 gigabit or even more, a standard Linux driver, so a standard network adapter using a standard driver from Linux, for instance, cannot keep up with the traffic rate, because a standard driver has not been designed to capture promiscuous traffic to monitor a network. A standard driver has been designed to provide connectivity to the machine with an average packet size which is usually big, with the traffic rate which is usually not exceeding a certain threshold. So if you want to monitor a network, you need optimized drivers. So we created a pfring, which is a framework, let's say a kernel module and a driver and a library that our applications use, like ntopng and ntopng use to capture the traffic at high rate. And this can work with standard adapters and standard drivers up to, let's say, 1.5 gigabit per second, depending on the hardware and on the traffic, on the average packet size, let's say. But we also support accelerated drivers. Let's say we created accelerated drivers for standard adapters like Intel or Mellanox, or we support specialized adapters to be able to scale and capture up to 100 gigabit per second. So if you install ntopng on Linux, pfring is installed as a dependency, and there is a service which is run automatically when you install the package. You should be able to check the status of this service using system control. So the standard tool that you have on Linux, it used also to control ntopng. Let me show you. Enlarge a little bit. So you can do system control, status, pfring, and you can see that there is a service running for pfring. And with the pfring package, you also distribute companion tools like pfcount, which are really useful to when you have to check that everything is running, if you want to check if there is traffic on the interface, what is the traffic rate. So for instance, if you want to run pfcount, you can get a network interface and run pfcount-i network interface. And this will print traffic statistics on that interface. As you can see, there is a little traffic in this case. So this is usually the first command that we use when we have to size the system. Before running ntopng, we check on the network interface what is the traffic that we have. Then there are, as I said, if you have to scale at 10 gigabit or more, up to 100 gigabit, you can use zero copy drivers, which are accelerated drivers that just skip all the operating system, so they bypass the kernel and provides optimal maximum capture performance. So we support Intel, Mellanox, Napatech, Silicon, Fiberblades. We support many adapters. And if you have to configure ntopng on top of those adapters, you don't need to do anything special. You just have to specify the interface name, and we have the drivers for all those adapters. Let's talk a little bit also about the CPU. So when you run ntopng and mprobe or multiple mprobe instances, you have to pay attention to what we call the core affinity. So if you have a modern CPU, you have for sure multiple CPU cores. And when you run the application, again, especially when you run multiple instances of our applications, you have to pay attention to the affinity to the cores, because you don't want multiple applications to run on the same CPU core, sharing the same CPU and delivering low performance, let's say. What you want to do is to run each application instance to a different CPU core. And you can do this using, for instance, in mprobe, we have this CPU affinity option where you specify the CPU core. If you have 8 cores, for instance, the core ID starts from 0, and then it's 0, 1, 2, 3, up to 7. So if you have, for instance, 4 mprobe instances, you specify CPU affinity 0 on the first instance, 1 on the second instance, 2, and 3. You can check the cores that you have on your machine, checking the CPU model or checking this approach file system. So for instance, if I run this command, I guess you already know your CPU model, but with this command you will get it. So this is Xeon E2136. You can open your browser. If we look for this CPU model, we usually get the Interlark website where we can see what are the specs for this CPU. So here we see that we have 6 cores with this gigahertz per second, and then we see what is the maximum number of memory channels. This is an information that we will use soon. So we know that we have 6 cores. We can also use this command to check the number of cores. So we read proc CPU info, grep processor, and we see that we have, in this case, actually 12 cores because this CPU is running hyperthreading. So this is 6 physical cores, sorry, 6 physical cores and 6 logical cores. And we can use those core IDs to set the affinity for the application. Now, there are other technologies that we can use. I don't want to bother you with too many concepts, but just to introduce you these, there are technologies which are used to distribute the traffic when you have high rate traffic to multiple CPU cores by using multiple queues. So for instance, if you have a single network interface, but the traffic rate is too high, you cannot handle that using a single mprobe instance, for instance, you can split this traffic into multiple streams using multiple queues, send this traffic to multiple application instances, and run each instance to a different CPU core. This is, this is what we call RSS. So RSS is another hardware technology which is used to distribute the load to multiple queues, let's say. So for instance, if we run ntopng, we usually run ntopng on top of a network interface, as we've seen. So you specify ntopng-i eth1. So ntopng will capture the traffic from this interface, and it is working fine up to 1, 2, 3 gigabit per second. Again, depending on the hardware specs, depending on the traffic that you have, etc. Now, if you are losing traffic because you have too much traffic and ntopng cannot handle that, you probably want to configure zero copy driver. If you have an Intel adapter or a Mellanox, you can configure the zero copy driver, or if you have an FPGA adapter like Napatech or Silicon Fiber Blades, you can use them. In order to enable zero copy on Intel, for instance, you specify the interface ETH1, but with the zero copy prefix after enabling the driver, of course, after installing the driver. In this case, as you can see from the picture, ntopng is bypassing the Linux kernel, so you get max capture performance, so you improve the performance. If this is not enough, because the capture thread in ntopng, which is running on a single CPU core, cannot keep up with the traffic rate, you can use RSS. So in essence, you configure the adapter to distribute the load using multiple streams, and you configure ntopng to capture from all of them. This will use multiple threads, so multiple cores, to capture the traffic. This lets you scale with the performance. So for instance, in this case, we have the adapter ETH1, we enable the zero copy driver, and we enable RSS with two streams, 0 and 1. So we are configuring ntopng to run one thread, one capture thread on stream 0 and another on stream 1. And then we tell ntopng to aggregate all the traffic information extracted from all the network interfaces, so ETH1 at 0 and ETH1 at 2, in a single view. So this is a way to configure ntopng and scale with the performance. And the same, we can do the same with mprob, for instance. So we can configure mprob on ETH1 Q0, another mprob on Q1, 3, 2, and 3. So we have 4 mprobs sharing the traffic from the same interface. We set the affinity to different CPU cores to make sure that each mprob is running on a single probe, separated probe, a single core, sorry, on a separated core, and they don't interfere with each other. And we can send the traffic information to the same 0MQ endpoint where ntopng will receive the traffic. Okay, this is just an example to show you how to configure the adapter with a certain number of queues. So for instance, in this case, we are using this tool to configure the driver with 4 RS queues to run mprob with 4 RSS queues. See, there is a question. We knew where to disk store its data. How about ntopng mprob and ClickHouse? Okay, so let me show you. Actually, let me come back here. Okay, if we come back to the user interface in ntopng, this is where ntdisk is storing the data if you enable ntdisk from using the simple, let's say, configuration in ntopng. You can change this path using the ntopng configuration file. There is an option for this. You can also change what is the root folder for ntopng. So this folder varlib ntopng. You can do this also using the ntopng configuration file. So if you run ntopng-h, you should see this option, which is the data directory. So this is how to configure where ntopng should store the data. Then you mentioned also ClickHouse, for instance. ClickHouse is an external process, so we usually don't provide configurations for ClickHouse, but in essence, you can go to etc ClickHouse server config.xml, and here you should find a path where ClickHouse is storing the data. I don't remember exactly the name of the configuration entry. Yeah, so this is the path you should change to change where ClickHouse is storing the data. This allows you to set, for instance, to add an additional hard disk and store the ClickHouse data to an external disk. The same for mprob. In mprob by default doesn't store data on disk unless you specify the option to store the data on file, for instance. And in that case, the option itself, you have to configure the path where you want to store the data in the option itself. Did I answer your question? You're welcome. Okay, so if we come back to the to the Intel website for our CPU, we have seen that we have here the maximum number of memory channels. This means that, in short, this means that this CPU can exchange data in parallel with two memory sticks, let's say, to make it simple. So this means that for optimal performance, we have to install on the system two memory sticks, or four, it depends on the hardware, but usually it's a good practice to put the same number of memory modules as the number of memory channels that you have here. And of course, if you have a system with multiple CPUs, you have to, and each CPU supports, for instance, two channels, you have to put two memory sticks per CPU. Now, there is a tool, which is dmidecode, that you can run on Linux to check what is the number of slots that you have for memories in your system and which one are populated. For instance, this is the first slot, and we see that the speed is unknown. This means that there is no memory stick here. In this case, the speed is populated, so we have the memory stick. We don't here, we have here. So we have two memory sticks on this system. If the number of channels is two, that's a good configuration. Then we have to also pay attention to the PCI bus. In fact, if we have, for instance, two CPUs and we want to run the software on the first CPU, we have to pay attention, make sure that the network adapter, also the right controller, if we dump traffic to disk, that they are in a PCI slot which is connected to the same CPU where we are running the software. In order to do this, we can use another software, another tool that we have on Linux, which is ls-topo. If we run this tool, we can see that we have one CPU, which is a NUMA node here, with a certain number of CPU cores, and we have this network adapter connected to this CPU. Then we have another CPU with additional information here. So we have to make sure that this adapter in this output is under the first node if you want to run the software in the first node. So probably a good configuration here if we run a probe on this interface, for instance, is to use as CPU core one of those, so 0 or 1 or 2 or 3. So this is an example of a wrong configuration. So we have the network interface on the first CPU, which is that we use for capturing the traffic. This traffic is copied by the network adapter into this memory, but then we run and probe on the second CPU. And this means that this traffic is crossing the interconnection bus that we have here in the CPUs, which is a QPI, which is adding latencies and leading to packet loss in essence. So in this case, we have a bottleneck here and we have performance issue. The best configuration would be to just change the affinity, the core affinity, using this parameter that we have seen, setting the affinity to core 0, for instance, which is running the first CPU. In this case, everything is local to the same CPU. We are not crossing the QPI bus and the performance are optimal. Yeah, that's everything for today. Do you have any question?